What I'd like to do now is talk about how we can apply TimedMemoizerEx to our running example, which is the PrimeChecker app. So this particular approach shows how we can use the TimedMemoizerEx class to check if n random numbers are prime. We've looked at this app many times now. I think this is probably the fourth time, maybe even the fifth time that we've taken a look at how this particular app works. Remember, it's an embarrassingly parallel app that's compute bound. As always, we have a main activity that keeps track of is used to compute the primality of n random numbers. And this particular implementation is going to be the one using the executor completion service with a thread pool and a prime callable class. Just for kicks, just to do something a little different here, because we've been looking at the same example over and over again, what we're going to do is we're going to use a work stealing thread pool, basically a fork join pool here. And this work stealing pool is going to be used to essentially provide the thread pool. And it's going to start out with the number of processor cores, because that's what a work stealing thread pool does. This particular example doesn't, well, maybe it illustrates the benefit of the work stealing pool, but it's probably not the best example of it, but it's kind of fun. So we have the TimedMemoizerEx that we just looked at, and we have our prime callable class, which is what's going to implement the callable interface. And that then can be used to submit it to the Java executor completion service framework, which will then use the fork join pool, the work stealing pool, in order to be able to process the requests in the pool of threads. Here's the constructor that's going to go ahead and stash away the function, which is the PrimeChecker function that's passed as a parameter, which will be the one using the memoizer, of course. And here's the call hook method that's going to run in a thread in the thread pool and in the fork join pool. And that particular method will then check to see if the number is prime, and it'll return 0 if it is. Otherwise, it'll return the smallest factor if it's not. And keep in mind that this apply method is what we're going to be able to transparently optimize by using TimedMemoizerEx, as we will see in just a moment. The call method returns a prime result, so you can associate the prime candidate with whether or not it's a prime number or not. Here's the main program, part of the main activity. It's the start computations method in the main activity. And it goes ahead and it creates a new timed memoizer, passing in the brute force checker, although of course it's trivial to change that to a more efficient checker if we want. And then we also give it the time out in milliseconds, which is the count of the number of elements, the number of entries we're going to check to see if they're prime, times 0.5 seconds. So that's the timeout period. And I just put that down. If you run the program, it was just so that it would do something interesting and run periodically. We then go ahead and go into the main processing stream where we generate count random numbers within a range intended to generate duplicate values. We transform each of those values into a prime callable, and we pass in the timed memoizer. And because it implements function, we can use it wherever a function is expected. And then we go ahead and we submit each of these value returning tasks for processing in the work stealing pool, in the fork join pool, not the common fork join pool, a fork join pool that we created specifically, which will have as many threads in the worker pool as there are cores on the processor. Since we're using the executor completion service, there's no need for a list of futures because that's all handled internally by executor completion service. We do need a background thread to run to reclaim the results. So we go ahead and make a new instance of completion runnable. We create a new thread and we start that thread. So now it's running in the background, essentially reaping the threads. And then if you take a look here, you can see what completion runnable has its implementation defined as. It implements a runnable, and then it just iterates through the results from I equals 0, I is less than count. And it calls the take method on the executor completion service. And whenever another result's available, it gets it. Take might block if there's no result computed yet. Get will never block because you don't end up in the completion queue unless you're done. And then it processes the results and prints them. And then there's the retained state stuff I've talked about before. I'm going to kind of skip through that pretty fast because it's something we've covered earlier, and it doesn't really matter for the discussion of the concurrency part here. So that's the end of our example that applies the TimedMemoizerEx to PrimeChecker. It looks pretty much the same as before, the main difference being that we're now using the TimedMemoizerEx, which will be more efficient in terms of how it's handling the various processing and the various results.